Hello and welcome back. In this video we're going to find the absolute max and absolute min given the algebraic version of a function. So the method we're going to use is to 1. Evaluate the function at all critical numbers. Remember, critical numbers means candidate x values for local maxes and local mins. These will also be candidates for the absolute max and absolute min as well. And evaluate the function at the endpoints. That's going to be all of the possible places where we could have an absolute max or an absolute min. Then we're going to take the largest and smallest of these values to get the absolute max in the largest case and the absolute min in the smallest case. Let's look at an example first before we head into the algebra. So we've got a function that's graphed over to the right, and you can see that the endpoints are at the beginning and the end of the interval from -2 to 6. Those are candidates for having absolute maxes and mins. And then the critical points are going to happen at the peaks and the valleys at the very least. We might have some more critical points, but at least at the peaks and the valleys. So our absolute max and absolute min are going to be among these. Whichever is the biggest, which is the peak right here at -0.5 roughly, that's going to be the absolute max. And whatever is the smallest of these y values, which happens at this local min at -2, or with a y value of -2, that is going to be the absolute min. All right, let me just write down there. The dots here are the critical points, and then the orange dots are the endpoints. So for example 2, it says find the absolute max and absolute min values of f of x equals 10x times quantity 2 minus ln x on the interval from 1 to e squared, including the endpoints. This is critical, no pun intended, because then we can use the extreme value theorem that we were just looking at a moment ago, saying that we're guaranteed to have the absolute max somewhere in that closed interval. All right, so we're going to first find the first derivative. We need to do that so we can find the critical points. And the first derivative here is going to involve a product rule. So we got the product of these two functions. Here's the first times the derivative of the second, which will be -1 over x, plus the derivative of the first, which is 10, times the second, which is 2 minus ln x. The x's cancel, so you get -10. The 10 will distribute to get 20 minus 10 ln x. Then it simplifies to 10 minus 10 ln x, and we'll go ahead and factor out a 10. That'll be good. All right, now we want to figure out where the first derivative is 0 and where the first derivative does not exist. Use my shorthand notation rather than writing all of the parentheses x's. Well, it's going to be 0 when that function is equal to 0. So we get 1 minus ln x equals 0, ln x equals 1. If we apply the exponential to both sides, we get x equals e. Or just think it's ln of e that's equal to 1. Now the first derivative does not exist in many different places. It doesn't exist at x equals 0 or any negative numbers as well. But notice that our interval is from 1 to e squared. So we're not really concerned about those places where the first derivative does not exist, because those are never in this interval. So we're just going to write none here with the understanding that this means none in the interval from 1 to e squared. Okay, now the next step is going to be to make a little table of values. In one column we'll write our inputs, In the other column, we'll write our outputs, f of x. And then what we're going to do is put all of the critical numbers that we found, which was just e, right? That was the only critical number that we found. That's the only x value where the first derivative was equal to 0, or dne. And I should mention that if you plug in e into the function, you do get a y value. You'll find that out in just a second when we plug e into the function. But if we plugged the x value into the function and we didn't get a y value, well then we know that we don't have a critical number there. And you find that out anyway. So here's e. If we plug e into the function, we're going to get 10 times e, and then times 2 minus ln e. Ln e is 1, so we'll have 2 minus 1, which is 1, times 10e is 10e. We're getting this by plugging in e into the function. This is our critical number. Now we're going to look at our endpoints. The endpoints are 1 and e squared. We'll plug those into the function. So we've got 10 times 1, which is 10. And then here, ln 1 is 0. 2 minus 0 is 2. 2 times that 10 gives us 20. If you plug in e squared, ln e squared is 2. 2 minus 2 is 0, times whatever is 0. These are our endpoints. Now what we do is look at the largest of these values, which is going to be 10e. Remember, e is about 2.7. 2.7 times 10 is about 27. That's going to be bigger than 20 and 0. So this is our absolute max. Then we look at the smallest of the y values, and that's our absolute min. This is all confirmed by the graph down below. So the absolute min was 0, happens over at the right endpoint of e squared. E squared is a little bit bigger than 7. And then the absolute max is up there at 27-ish, and it happens around e, so around 2.7. There's your absolute max, happened at that critical number. Then this other point that we found was 1, 20. That was the first endpoint, but that one wasn't an absolute max or an absolute min. Great. Looking at example 3, it says find the absolute max and absolute min values of f of x equals x to the 2/3 on the interval from -2 to 3, closed interval. Here we're going to start with the first derivative again. We can clean this up a little bit. We can write 2 over 3 times the cube root of x. Figure out where that is equal to 0 and where it does not exist. Now the top can never be equal to 0, right? This fraction can never be equal to 0 because the top is never 0. So we would just say the first derivative is never equal to 0, so there aren't any x values where the first derivative is equal to 0. But there is an x value where the first derivative does not exist, and that's when the bottom is 0, and that happens at x equals 0. So we got our x value. Now we can take that and try to figure out where to put this. So here we have x and f of x. Here's the x equals 0 critical number that we found. If we plug that into the original function, we get 0 to the 2/3, which is 0. Then we can plug in the endpoints, which are -2 and 3. Now if we plug in -2, we're going to square that to give you 4, and then take the cube root of that. So this is the cube root of 4. If we plug in 3, we'll square that to give you 9. And then the cube root of 9 is the cube root of 9. Cube root of 27 is 3, but the cube root of 9 is just whatever. Cube root of 9 is some number. The absolute max will be the biggest of these, which is the cube root of 9. Without knowing what the numerical approximation is, that's the biggest of all these. And then the smallest of all these is the absolute min. And just to highlight them, I probably should have done that up here. I'll quickly highlight the absolute max and the absolute min. Let's highlight it for example 3. So for example 3, the absolute min is down here. There we go. And the absolute max is on the right endpoint. There we have it. Thanks for watching this video, and see you next time.